This script is going to walk you through a few examples of using the Metafor package in R. We'll start with some toy data just to get a sense of how the estimates from the meta-analysis compare to raw means, and then I'll actually apply the meta-analysis to some estimates from stochastic actor-oriented models. The first thing that we need to do is a few basic steps to prepare for the analyses. You'll want to start by setting your working directory to wherever the folder with the data is located. I created a folder on my desktop, so that's where I set my working directory. Then you want to load the library so that you can use the Metafor package. If you don't already have the package installed, you can install it with the install packages command. Next, read in the data from the example data text file. If we look at the data, we can see that I created 10 networks. There are estimates and standard errors for 4 fake variables that I created just to illustrate how the package works. And there are also estimates and standard errors for some real results from SIENA. These estimates and standard errors are for the outdegree parameter and the parameter for selecting a friend of the same gender. Finally, a variable with the label size indicates how many students are in each network. We'll use that data to create the objects that we need for our examples. Our first exercise is going to be looking at the difference between a raw mean and the estimate of a meta-analysis. This example is going to use data that is obviously made up, as you'll see in a second. So let's look at these data. And here's a scatter plot with the estimate value on the x-axis and the standard error value on the y-axis. The distribution of the estimates is symmetric around 0, and the standard errors are constant at 1. Next, we'll look at the raw mean. As you can see, it's 0, which you probably could have guessed after looking at the plot. Now we'll use the Metafor package, specifying that the estimate is our outcome, and the standard errors will be used to compute the known variance. This model is similar to the two-level unconditional model that I discussed in the slides. So the intercept is going to be our estimated mean of the parameter. In this case, the estimated mean from Metafor is the same as the raw mean. This is good. There's no reason for it to be different, and you shouldn't get counterintuitive results just because you applied a sophisticated method. In our next exercise, we're going to introduce an outlier into the data. Here are the data for the next exercise. And if we look at them, we'll see that the value for the last network now has an estimate of 20 and a standard error of 10. Here's what it looks like when we plot these data, again with the value of the estimate on the x-axis and the value of the standard error on the y-axis. When we calculate the raw mean of the estimates, we'll notice that it's larger than 9 of the 10 estimates. In fact, it's larger than all the estimates except for that outlier. When we use the Metafor package to estimate the mean, however, we're going to get a noticeably smaller value. Remember, the meta-analysis essentially weights each estimate inversely to its standard error. So the outlier estimate will count less if it also has a large standard error. In fact, if we compare the estimate from the meta-analysis to the mean of the other 9 estimates, we'll see that they're fairly similar. It's really important to emphasize that the outlier counts less toward the meta-analysis estimated mean in the example above only because the estimate has such a large standard error. Meta-analysis will not reduce the influence of outliers to that extent unless their standard errors are large. Consider the same data, but with the standard error of the outlier reduced, though still larger than the other standard errors. When we plot the data, it's going to look similar to the previous plot, but that's because the y-axis is scaled differently. This time, the outlier estimate has a standard error of 2 instead of 10. When we look at the raw mean of these estimates, it's the same as the previous raw mean because the standard error is the only thing that's changed. Next, we'll use the Metafor package to estimate the mean again. This time, the estimate of the mean is closer to the raw mean. This is because the value of the outlier is still much larger than the other values, but its standard error is only twice as large, instead of 10 times as large as the other standard errors. As a result, the estimate of the mean is slightly smaller than the raw mean, but the influence of the outlier on the estimated mean is clearly present. The point of this exercise is to demonstrate that meta-analysis does not automatically remove the influence of outliers. Instead, it's going to reduce the impact of any estimates with large standard errors, and if the outlier has a reasonable standard error, it may still impact the results quite a bit. Now, the above examples use fake data, where most estimates are symmetric and the standard errors are constant. You will likely not encounter real results that look anything like this. So here's another example, this time using data that are designed to look more like what you might see from a real analysis. Here are some of those data. When we plot these data, we see that there are 7 estimates that have relatively small standard errors, and then 3 other estimates that have relatively large standard errors. Unlike the other plots, however, the larger estimates and standard errors in this plot are not so large as to suggest an error in data entry or estimation. When we calculate the raw mean of these estimates, we'll notice that it's larger than 7 of the 10 estimates. This is not a problem in and of itself. After all, we are purposely calculating the mean of the data, not the median. But we might be concerned that the mean is being pulled to the right by estimates that have large standard errors, which means that we have less confidence in their accuracy. Next, we'll use the Metafor package to estimate the mean again. This time, the estimated mean is about half the size of the raw mean. This example illustrates one of the main advantages of using variance known models with real data. Because the variance known model is essentially weighting the estimates by their standard errors, the model produces an estimated mean that is closer to the mean of the estimates that are more precise. It does not discard the larger estimates, but since they have larger standard errors, the model predicts that the true value of the mean in the population is more likely to be near the estimates that were estimated more precisely. For the next exercise, we're going to look at real estimates and standard errors from SIENA. These particular estimates are taken from a paper published in Sociological Methods in Research, where we examined how stochastic actor-oriented model estimates of peer influence from our SIENA compared to estimates from other methods. Here are our raw data. Here are the estimates and their standard errors, and we'll also list the size of each network. The out-degree density coefficients reflect the overall rate of friendship choice. They can be described as representing the overall probability and log odds of selecting any random individual as a friend, adjusting for other covariates in the model. This scatter plot displays the size of the coefficient on the x-axis and the size of the standard error on the y-axis. Now, at first glance, it might look like there's a little bit of a trend where the estimates that are more negative on the left side of the plot have smaller standard errors, but it's important to look at the scale. There's really not too much of a difference here in the size of these standard errors. Next, we'll look at the raw mean of the estimates. And then we'll use Metafor. When we use this package, the intercept will be the estimated mean that is adjusted by the size of the standard errors. This estimated mean is almost the same as the raw mean. This confirms that there wasn't much variation in the size of the standard errors, which is why the estimated mean is not much different. Let's look at another plot. This time, the coefficient for out degree is on the x-axis, and the size of the network is on the y-axis. It looks like there's a relatively linear pattern. The estimates that are closer to 0 appear to be from smaller networks, and the estimates that are more negative are from larger networks. Also, unlike the previous plot, there might be some meaningful variability in the size of the networks, as they range from around 150 students to almost 450 students. So let's estimate the mean again, this time including network size as a covariate. The intercept is still going to be our estimated mean, but this time it's different from the raw mean. Now, it's going to be our estimated mean of out degree when network size is 0, so it's probably not interpretable at that value. We also have statistically significant negative estimate for our size covariate, which indicates how much we expect out degree to change with each 1 unit increase in the network size covariate. So what do we learn from this? First, the raw mean and the unconditional meta-analysis estimate are nearly identical. This means that adjusting for the size of the standard errors had little impact on the size of the estimated mean. Second, the size of the network is a significant predictor of out degree. The magnitude of this effect is a little bit difficult to judge because the coefficient appears small, but that's because it is the change associated with a one-person increase in network size, and the outcome is in log odds, which are rarely easy to interpret. But the estimate is a significant predictor, suggesting that increases in network size are associated with decreases in the magnitude of the out degree coefficient. If you think about this, it makes perfect sense. If out degree represents the overall probability of selecting any random individual as a friend, then this probability of selecting a friend at random should be smaller in larger networks. We're going to do one more example. This time, the same gender coefficient is going to reflect the log odds of naming a friend of the same gender, adjusting for other covariates in the model. Here are the estimates and their standard errors, and the sizes of each network again. This scatter plot displays the size of the coefficient on the x-axis and the size of the standard error on the y-axis. At first glance, it doesn't seem like there are any obvious patterns. Here's the raw mean of the estimates. And now let's look at the estimated mean. The estimated mean is almost the same as the raw mean. When we look at the plot that includes the estimate on the x-axis and the size on the y-axis, it's not clear that there's any association between the estimates and the network size. So let's estimate the mean again, this time including network size as a covariate. Unlike the results for outdegree, the estimated mean of same gender barely changes. And the estimate for the network size covariate is extremely small and almost at zero, with a small confidence interval around zero. So in this case, the estimated mean of the same gender coefficient is really not very different from the raw mean. And it also does not seem to be dependent on the size of the network. This suggests that the preference to select friends of the same gender does not vary systematically based on the size of the network. That concludes this example script. I hope this was helpful, and please feel free to reach out if you have any other questions.